Here we talk about the electric field inside and outside a spherical shell with a charge that is uniformly distributed on it. It's not necessary that it is a conducting shell, in which case this will be electric field will be zero inside here. It is a shell anyway, so it doesn't matter whether it is a conductor or a dielectric. I think that's the way to say that a shell, a conductor will always be on a surface if it's on a solid material, but it is given that it is it's a thin material which only has a shell. So so if I were to draw the sphere, so we have this represents the spherical shell, and since it is a thin shell, all the charges are on the outside. By spherical symmetry, we argue that whether you stay here or there, the physical quantity should look very similar. So if they are radially outward, they will all look like this. So that's your electric field lines. They all are radially outward. Let's, the first part talks about in 10 centimeter, and the radius r of the sphere is 15 centimeters. So r is 15 centimeters, so that's it. R equal to 15 centimeters. One of the point is inside and one of the point is outside. The interesting part is when you're outside the sphere, the electric field is, for any spherical distribution, the electric field is exactly that of a point charge. So when you're outside, you're in its electric field direction is r hat, and it is 1 over 4 pi epsilon naught. And the total charge on this, let's say, is Q, which is 32.2 microcoulomb. So that's your Q, and that's Q over how far you're from it, from the sphere. So that's r squared. That's not the capital R, that's the radius of the sphere. This is how far you're from the center. And that's when you're outside. If you're inside the sphere, if it was a solid sphere, then the electric field linearly increases and reaches the max and then dies down as 1 over r squared. But inside the sphere, if I were to have a Gaussian sphere enclosed inside the sphere, there is no charge inside, so this will be 0 inside. So if I were to plot the electric field, so if I were to plot the electric field, let's say the magnitude of the electric field is being plotted. It is 0 everywhere inside until radius r, and from that point on, so it's 0 everywhere here, and then dies down as 1 over r squared. So 10 centimeter is inside and 22 centimeter is outside. So let's answer part A to the problem. So electric field inside the sphere is exactly 0. So that's an easy part. And part B, it's outside, then you act as if it's a point charge. So it doesn't depend on the radius r at all. So electric field is equal to r hat, it's pointing outward, and K is 8.99, so 1 over 4 pi epsilon naught, so it stays 8.99 into 10 raised to 9 times Q, which is 32.2 microcoulomb, so it's 10 raised to minus 6 coulomb, divided by r squared, which is now 22.0 into 10 raised to minus 2 squared. That's proof of that. And this is 82. Let's see, it's 8.99 into 32.2 divided by 22 squared is equal to 0.598, 3 digits into 10 raised to, so that is a 9, that is a 10 raised to minus 6, and that is a 10 raised to minus 4. And the unit is Newton per Coulomb. So that gives you 10 raised to minus 2 in the numerator. So that's 10 raised to 7. And I can use that to make it 5.98 into 10 raised to 6 newtons per Coulomb. So that's the magnitude of the electric field outside. And 22 centimeters is about 1.5 times the radius. So that's somewhere here. So that's a trick of field. That's the solution to this, and I hope this helps, and I'll stop the recording at this point.